Welcome back. Today or in this lecture, we're going to be looking at the first three sections from chapter 3 of the book, which lead up to the simplex method, which, as we've talked about, is the way that we solve linear programs. First, we're going to put a couple of conditions on our linear program, at least for now, for the simplex form. We're going for the simplex method. We're going to be relaxing these in the future, but for now, we're going to put a couple of conditions on it. First, we're going to say that all constraints are equations with non-negative right-hand side. And secondly, we're going to say that all variables are non-negative. So what does this mean? Well, this means we have to introduce something called slack variables, or similarly, surplus variables. What is a slack variable? Well, a slack variable is remember we're starting with inequalities. So for these inequalities, what we're doing is we're going to add this artificial variable in each of them to take up that extra room. So here's the example. This is the linear program that we dealt with in last lecture. Take your first equation. x1 minus 2x2 is less than or equal to 12. What we do is we convert this to an equality and we add in a slack variable. So that becomes this, minus x1 minus 2x2 plus s1 is equal to 12. Okay. So we have put in a new variable to take up the excess space in there. The second equation says that 2x1 plus 3x2 is greater than or equal to 18. We add a surplus variable there. So we subtract something to make it equal to 18 because the left-hand side was bigger. And then we make all of our variables greater than or equal to 0. This should actually say s1 greater than or equal to 0 and s2 greater than or equal to 0. So all of our variables are also non-negative. So that's the idea of a slack or surplus variable. It's just this new variable that we introduce to take up the difference in an equality, and we either add it or subtract it depending on which direction the inequality sign is. We also have to deal sometimes with unrestricted variables. The second condition for our simplex method says that all variables have to be non-negative. Sometimes we get an unrestricted variable, something that could be positive or negative. So in that case, what do we do? Well, here's an example. We have an equation where x is unrestricted, but y is non-negative. So for x, what we do is we change x. We say that x equals a minus b with a greater than or equal to 0 and b greater than or equal to 0. And if you think about it, what this is doing is it's introducing two variables, both of which we can say have to be positive, and replacing our unrestricted variable. So now we get something where all of our variables are non-negative, and then we would take that the next step and say this becomes 7a minus 7b minus 5y plus s equals 4 with a, b, y, and s, our slack variable, all greater than or equal to 0. So those are two adjustments that we have to make first before we jump into the simplex method. There's going to be some other cases that we have to deal with, but this gets us started. So let's take a look back at our graphical solution that we saw in one of the earlier classes. We saw that when we're dealing with the graphical solution, really what we have is that the solutions are going to be at the vertices, at the corners of our feasible region. So this was the one that we saw in an earlier lecture, and we saw that the solution ended up being right there. Now here I've just rewritten my linear program with slack variables. So what have I done? I've introduced a new variable for every equation. This is giving me more variables than equations now, than constraints. Okay, that's going to be an important point. We have to have more, we're going to be looking for more variables than we have constraints. Think about what these slack variables do now. Take any of the corners in here. Say we take our first corner, 0, 0. What do we have here? We have x1 equals 0, x2 equals 0, and our slack variables are non-negative values. So S1 equals 32, S2 equals S1 equals 32, S2 equals 40, and S3 equals 30. Okay, I get those just by plugging in x1 equals 0, x2 equals 0 in the three equations, because now I don't have inequalities, but I have equations for my constraints. Go up to another corner, say we go here. What do we have? Well, if you start to look at the point 8, 0, here x1 equals 8, x2 equals 0, you are going to have x2 equals 0, as we noted, but you are also going to have, well, that is this equation for, which is our first constraint. The slack variable in there is S1. This point is going to give you S1 equals 0. We had x1 equals 8. And you can see this again. Take x1 equals 8, x2 equals 0, plug it into your constraint equalities, and you're going to see that S1 is equal to 0. S2 and S3 are going to be other values. But the key thing to note here is that every corner is going to have, in this case, it's going to have two of our equations, or two of our variables, equal to 0. And what we're going to see is that if we have 5 variables, a corner is going to have 5 variables equal to 0. If we have 3 variables, then a corner is going to have 3 of our variables, including our slack variables. 3 of them are going to be equal to 0 at all the corners. That is a very important thing to note when we're dealing with the simplex method or with a graphical solution. 2 variables means we are setting two variables originally, means that we're setting 2 of our overall variables plus slack variables equal to 0. And that gives us a corner. So what we're doing is we're transitioning from this idea of the graphical solution to an algebraic solution. So in the graphical solution, what did we do? We graphed constraints. The solution space is infinitely many feasible points. In an algebraic solution, we have m non-negative variables with n equations with m less than or equal to n. Sorry, I just realized this is backwards. It is m greater than n. We have more variables than equations, but we have infinitely many feasible solutions. So graphically, next thing we do is we identify the feasible corner points. We find all those corner points, and these are the candidates. With algebraic, we're going to find something called basic feasible solutions, and this is the equivalent of corner points in the graph. Those are our candidates. Finally, with graphing, we use the objective function to sift through all the possibilities and find the one that works. It's the same thing in algebraic. We use the objective function to find the one that works. So we have the idea of a basic solution when we're dealing with algebraic. This is the equivalent of a corner in our graphical solution. Basic solutions are determined by setting n minus m variables equal to 0 and solving the rest of the equations. So, for instance, in here, we have 3 equations, 5 variables. Okay, we count the slack variables. What we're going to do is we're going to set 2 variables equal to 0. Then what are we left with? We're left with 3 equations and 3 unknowns. If you recall from the linear algebra class, we can solve that. So that's what we're doing. The simplex method is simply solving systems of linear equations over and over and over again until we find the best solution. The trick is we're going to be smart about how we choose the corners. The simplex algorithm, so if you think about your graphical solution, one way of doing this would be to start at the origin, 0, 0, or any feasible point, at any basic point. Okay, so a basic point is where you have set some of your variables equal to 0 and you solve for the rest of them. The simplex algorithm, one of the ways you could do this is start at your basic feasible point 0, 0. It's usually the easiest one to start at, and just kind of hop around your feasible area until you find the best solution. The simplex algorithm essentially does that. It starts at 0, 0 or some other basic point, some other basic feasible point, so a basic point in the feasible region, and it hops from corner to corner to corner, always getting better until it finds the best solution. So, simplex algorithm. First thing in the simplex algorithm is to introduce your slack variables. So, when we're looking at this linear program, which we've seen before, the first step is introduce the slack variables. Now, what we're going to do is we're going to start with this. We are going to recognize that we have 5 variables and 3 equations. So the difference between that is 2. So we are going to set 2 variables equal to 0, and that leaves 3 variables. We have 3 equations, and we solve those 3 equations in 3 variables. But we don't do it explicitly every time by writing out equations. We're going to introduce something called the simplex tableau, which does exactly that with a couple of rules. So here's the simplex tableau. Here is our linear program. What we do is we create a column and call it basic, and I'm going to talk about basic in a minute. A column for our z variable, what we're trying to optimize. Now that is going to just stay there. We don't count z as being one of our variables that we can change. Okay, when we count the number of variables we have, we count the starting variables and the slack variables. We add a column for each of our variables. In this case, the 2 variables we started with, the 3 slack variables. And then there is a solution column at the end. And now we put in 1 row for our objective function. And notice what we've added in here are the coefficients. And 1 for each of our constraints. Now, notice when we do the slack variables, we have a unique variable in each constraint. Constraint 1 has S1, nobody else has it. Constraint 2 has S2, nobody else has it, so forth. Those variables, we call them basic variables. So to start with, our slack variables are usually our basic variables. Our others are non-basic variables. That is wrong. It should be that these 2 are the non-basic variables, not z. X1 and X2 are the non-basic variables. So if you think back to your linear algebra, we had the idea of basic variables and free variables. Free variables were the things that you could set to whatever you wanted, and then you would calculate the basic variables. This is the same idea, with just a little extra on it. Here, our non-basic variables, we're going to say we set those to 0, and then our non-basic variable, or then our basic variables, we calculate them. So these are like our free variables, except that we say we're going to, for the freedom part of it, we say set them all to 0, calculate everything else. Okay, so essentially finding the easiest solution for it. Okay. Notice on the first column, we called it the basic column. There we list our basic variables. Note that our basic variables kind of form an identity matrix. So the S1 column and the S1 row has 1 in it. The S2 column and the S2 row has 1, and so on. Okay. So we want to keep track of our basic variables, so we put them in a special column over here. Now, we talked about how we start out by saying our non-basic variables are 0. So what's the value of our objective function here? Our objective function is 3x1 plus 5x2, that's equal to 0. That is right there. Okay. So keep that in mind, because we're going to see that our solution is going to appear in that far top right corner by the end of what we're doing. Okay, so that's our tableau. The tableau gives us the values of our coefficients. It helps us keep track of our basic variables, and it's going to keep track of our solution. Now, one thing to note is that depending on the book that you pick up, they will construct this tableau a little bit differently. There's also something called a compact tableau that looks much smaller, but at the end of the operation, they're all going to do the same thing, just sometimes with slightly different rules depending on how it's been set up. Okay. So we're going to consistently look at our tableau in this form. Like I said, if you pick up another book, it may look slightly different, but I can guarantee that what's happening in the background is the exact same thing. So now we have to iterate. What we have to do is essentially jump from corner to corner in our feasible region, where I'm going to use a two-dimensional graph, a two-dimensional area here, so we can kind of see what's happening and get a bit of an understanding of what's going to happen. What we're going to do to jump from one to the other, we're going to exchange a basic and a non-basic variable. In other words, our non-basic variables, we're saying that these are our free variables, but we're going to set them to 0. What we're going to do is we're going to take one of those non-basic variables and say, I'm going to set this to a different value, and I'm going to take one of my basic variables, that was something else, and set that to 0. And I'm just going to exchange those two. And if you're smart about how you exchange them, what you're going to do is jump from corner to corner in an efficient way. So here's the rule, and we're going to just do a set of rules over and over again until we find our solution. So the rule is, look at your non-basic variables, in this case x1 and x2, find the value in the z row that is the most negative. Some of these may be positive. You only want to look at the negative ones. In this case, you have -3 and -5. The -5 is the most negative one. That's what we're going to use. That is going to be called the entering variable. So in other words, we're now going to go from this corner where x1 and x2 is 0, and we're going to give x2 a value. x1 is going to stay at 0. So what happens when we do that? That means we're moving someplace up here. x2 is going to be non-negative. We're going to move to a corner up along that that axis. Now, I talked about how this is trading a non-basic and a basic variable. We've found a non-basic variable that we're going to trade out. So we have to find a basic variable to pull in to exchange with it. And here is where we find the condition to do it. We have found our entering variable. So x2 is our entering variable. It is going to enter the basis. It's going to become a basic variable. We have to find the leaving variable. And for that, we use something called a simplex optimality condition. We have three candidates, S1, S2, and S3. It could be any one of them, but here's how we choose. Choose the variable for which the ratio of the solution to the corresponding positive constraint coefficient under the entering variable is smallest. So in other words, you look down the row, or down the columns. This column and this column. And you divide. 32 divided by 4. See, that's the S1. That's the S1 row. So the value for S1 is 32 over 2, which is equal to 16. Do it for all of them. 40 divided by 4, and that's the S2 row. So S2 is 40 over 4, which equals 10. The S3 row is 30 divided by 4. 30 divided by 4 equals 7.5. Then you take the smallest one. And that becomes your leaving variable. So you're going to make S3 equal to 0, and you're going to make S2 equal to something other than 0. Now keep in mind one thing to note here, which doesn't happen in this exact thing. Positive constraint. If one of these numbers is negative, you ignore it. So this, you only look at positive numbers. You take the smallest one, but you take the smallest positive one. If something is negative, you don't take it. You ignore anything in that in the x2 column, in the column of your entering variable that is negative. Okay. So we've identified that x2 is our entering variable and S3 is our leaving variable. So here's what we have. We have this is the basic point where we start. What we're doing is we're setting S3, we're going to say S3 is now equal to 0 and X1 is now equal to 0. Well, where's S3? S3 was in this equation, our third constraint. Which one is that? That is this line. So notice what we're doing is we're jumping from here up to here. Now, what would have happened if we had tried to trade a different variable? Remember, we went for the smallest ratio. If we had tried to take a bigger one, we would have jumped up to here or up to here. We would have jumped up to the intersection of a line that is outside our feasible region. By going to the smallest one, what we're doing is we are moving our objective function as far as we possibly can without leaving the feasible region. And that's an important thing to note. By taking this smallest number, the smallest ratio, you don't leave the feasible region. You just jump to the next corner in the feasible region. Okay, so we have identified now our entering variable and our leaving variable. Now we have to exchange them. So just a bit of terminology. X2 was our entering variable. We call that our pivot column, the S2. S3 is the leaving variable. So we find the row that has S3, that represents S3, and that is our pivot row. The intersection of that, we call it our pivot element. Okay? And that pivot element is going to be important in the rules that we're going to see in just 1 minute. Now we've identified our pivot element, pivot row, and pivot column. What do? Here is our iteration. Here is how we take our tableau and change it around so that it now represents that corner. So you could imagine if you had the equations, what we've done now is we've said leave S1 equal X1, leave X1 equal to 0. We're going to set S3 equal to 0. That was our leaving variable. We could now go back to our equations and solve for X2, S1, and S2. What we're going to do is I'm going to give you some rules on the tableau that does just that without having to go through solving all the equations. Okay? They're messy, and this is why we use an Excel solver or some other solver almost all the time, but it's a good practice to try it once or twice just to see how this works and just how messy it is. So we have two rules. First rule involves our pivot row. We replace the leaving variable in the basic column with the entering variable. That's in the leftmost column. So we just say take X, in this case, take X2 out, replace it with S3. Then for the rest of that row, the rest of that row becomes the current pivot row divided by the pivot element. The rest of it, every other row, the row becomes the current row minus the pivot column coefficient times the new pivot row. Now, let's see what this actually means. Let's go through an iteration of our Gauss-Jordan method, which is our simplex method. So here is the tableau that we started with. What do? It says take our tableau, we're going to redo it, Z, X1, X2, S1, S2, S3, and solution. It says first thing, in our basic row, take out the leaving variable and put in the entering variable. So if we recall, we had X2 was our entering variable, S3 was our leaving variable. So this becomes Z, S1, S2, X2. We replace it. This is our pivot row. This is our, let me do it this way. Highlight it. This is our pivot row. This is our pivot column. Okay, so our pivot element is 4. So here's what we do. First off, we start with our pivot row. And we take our entire pivot row, and the rule says to take this row and divide by the pivot element. So this whole row, our pivot element is 4. Every element in here, we divide by 4. So going across, we had a 0. 0 divided by 4 is 0. We have a 2. 2 divided by 4 is 1/2. 4 divided by 4 is 1. 0 divided by 4 is 0. 0 divided by 4 is 0. 1 divided by 4 is 1/4. 30 divided by 4, 30/4, or 15/2. Or 7.5, however you want to represent it. Okay, so there's our pivot row. That's the easy one. What about the others? Well, that gets a little bit more complex. The rule now says, take the row So we're going to take our Z row. This applies for all rows, including the Z row. We're going to take our Z row, which is, I'm going to write it like this: 1 minus 3 minus 5, 0, 0, 0, 0, including the solution. Okay. Subtract from it the coefficient in the pivot column. So that row in the pivot column has the number 5. So it's minus -5 times the new row, the one that we just calculated, the new pivot row, times 0, 1/2, 1, 0, 0, 1/4, 15/2. Okay. And now go through element by element to get our new values. So minus times -5, that's +5. So it becomes +5 times that row. So 1 plus 5 times 0 is 1. -3 plus 5 times 1/2, that's -6/2 plus 5/2. That becomes -1/2. The next one is -5 plus 5 times 1 is 0. We get a couple of zeros because it's all zeros. We get 0 plus 5/4 becomes 5/4. And 0 plus 5 times 15/2, that is 75/2. That is our new Z row. So the Z row becomes 1, -1/2, 0, 0, 0, 5/4, and 75/2. There is our new Z row. But our next one, S1. So S1, our original S1 row was 0, 4, 2, 1, 0, 0, 32. The coefficient in that row in our pivot column is 2. So it's -2 times our new pivot row. 0, 1/2, 1, 0, 0, 1/4, 15/2. So what do we get when we add these up? We get 0. 4 minus 2 times 1/2 becomes 3. 2 minus 2 times 1 is 0. That is a 1 and a 0. This is 0 times -2 times 1/4 becomes -1/2. This becomes 32 minus 15, which becomes 17. So that row becomes 0, 3, 1, 0, 3, 0, 1, 0, -1/2, and 17. Kind of tedious. Now I've run out of room for the calculation, so I'm just going to write down if you take S2 and do the same thing. So it will be the S2 row minus 4, because that's the coefficient in that row in the pivot column. So the S2 row minus 4 times our new X2 row, we would get 0, 2, 0, 0, 1, -1, and 10. And there is our new tableau. What this represents now is the value at our second corner. So remember, that was the second corner going up. What does this say? This says that our non-basic variables are now x1 and s3. Those we're setting equal to 0. We have our basic variables are s1, s2, and x2. And if you look at it, s1 has 1, 0, 0, s2 has 0, 1, 0, x2 has 0, 0, 1. So you've kind of got an identity matrix, a permuted identity matrix sitting in there. Those are our non-zero values. But what we have is that at that corner, remember, this is all about trying to get our objective function as big as possible. At that corner, our objective function is now equal to 75 over 2, or 37.5. So the tableau, when you've gone through this, tells you what values are 0, what the values of your variables are. That's what this final column is. That's the values of our variables at that corner, and what the value of our objective function is. So now, we found that. What do we have to do? We have to identify we have to do the same thing again. So we identify our non-basic variables. That would be x1 and s3. Find the biggest negative value in the z. So you look at the z value for your x1 and your s3. I accidentally erased a number here. So the x1 value is -1/2. The s3 value is 5 over 4. That means our new entering variable is going to be x1. What about our leaving variable? Well, we have to do those ratios again. So you do the ratio of 17 over 3, 10 over 2, and 15 over 2 divided by 1/2. What do you end up with? You end up with S1 being the new leaving variable. Oh, here, I've redone it here. So we have x1 is our new entering variable. We do our ratios. S1 is 17 over 3. S2 is 10 over 2, which is equal to 5. And S3 is 7.5 over 0.5, which is equal to 15. The 7.3, 17 over 3 is 5 2/3. So actually it's S2 that gets introduced. So again, we do the same thing. Here is our pivot column. Here is our pivot row. We swap everything out, and I'm not going to go through all of the details of the calculations, but at the end, after you do the calculations, you get this, where your S1, X1, and X2 are your basic variables. So the solution now, when you look, so now when you look across here, what do you have? You have your non-basic variables being there. There's no more negative numbers on the Z row. When that happens, you're done. You have found your optimal point. So the rule is you keep doing these iterations until you have no more negative numbers on your Z row for your variables. At this point, what do we have? We have a solution equal to 40. We have S1 is equal to 2. We have X1 equal to 5. X2 equal to 5. And if you recall from our graph, and when we solved this last time, we had said X1 equals 5, X2 equals 5, and Z equals 40 was our solution. We have found the exact same solution with the simplex method, and we've done it by hopping from corner to corner. Now, when you are dealing in multiple dimensions, of course, you can't picture this graphically, but it's the same idea that happens. The simplex method solves linear programs by jumping from corner to corner until it has found a solution. So that's the simplex method. At this point, it's probably a good idea to try a couple of these by hand, see what's happening. There are also some solvers online for the simplex method that will show you all the iterative steps. So you don't have to do all the calculations, but you can still get an idea of what's happening. Exploring those might be a good idea. But that is the basis of the simplex method.